So our topic is the last topic. Today, the topic would be sets and set operations. This is due. Okay, kindly check online task due tomorrow. So two tasks are due for tomorrow. If you're not yet able to finish that, after this you can start. Okay, so make sure you submit your work before the deadline. Let's begin. So from sets to set operations today, our objective. Here is a summary of what we've been discussing in module number one, the nature and the nature and the usefulness of mathematics, its characteristics as a language. So from last meeting, we presented to you the grammar of mathematics, which is logic. I presented to you some ideas in logic. Okay, so mathematics is abstract, logical, rigorous, systematic, precise, generalizable, creative, and it is used as a tool by many fields, okay, in the sciences. So this is precise, okay. Ito pa. Blurry, slides are blurry, Manjot. Okay, let me reshare it. Pixelized. Okay, maybe the internet signal. Okay, let's proceed. So, for example, algebra, a field of mathematics. Okay, we use symbols, and then the symbols we can apply as properties. So that is a generalizable or a abstraction of the properties in arithmetic. Okay, it's also precise. We use exact language. Systematic, it builds on concepts. So let me emphasize something here. Okay, the notion of a set. Okay, what is a set? In mathematics, a set is a primitive term. It's a term that is agreed upon as simple enough not to require a definition, only a sense of a sense or notion of what it means. Okay, why do we need a primitive term? Well, if we define a concept using other terms or concepts, at some point there should be a very simple term that doesn't need any definition. So it's just the basis where we can build upon other concepts. Otherwise, there would be no end in the definition. So it should stop somewhere. And here it stops in this concept we call a set. So we don't say definition of a set, rather, we say it's the notion of a set. Our understanding is that it is a collection or a grouping of objects having a particular property grouped together. It also has objects, also called elements, which belongs to the particular collection. Okay, so let me emphasize another wording here. So the object is also referred to as the element or elements of the set. So using a short phrase, the notion of a set is this, underlined, it's a well-defined collection of objects. Okay, let's proceed. I'll clarify. That phrase, well-defined collection of objects, means that there is no ambiguity or vagueness on which the objects or elements belongs to or does not belong to the collection. I know what the objects belongs to or does not belong to the collection. So it's sort of a rule, okay? Well-defined collection of objects. I'll show you three statements. Okay, you can participate via the chats. What you need to do is simply say yes or no if the collection in statements 1, 2, 3 is considered a well-defined collection, thus a set. And then you just explain or justify why or why not. Okay, so let me check. We are 39 right now, including me. Okay, go ahead and respond to that question in the chat box. Which collection is considered a set or not a set? Justify. So again, as a reminder, when you're attending our online class, please focus on the online class. Do not do anything else. Go ahead, please, participants. Okay, from Manjot, 1 and 2, not a set. 3 is a set. How about the rest? Okay. Ano yung 1 and 3 na yan? A set. So, number and then answer and then justify. Okay, so for example, number 1 is not a set because, okay, there is a word there that is vague. Number 2 is not a set, and number 3 is a set. Okay, so number 3 is a set because we have the set of integers, this collection of numbers. 0, 1, 2, 3, and so on and so forth, -1, -2, -3, and so on and so forth. Okay, so I can enclose a collection. So these are the elements using a pair of curly brackets. Then I can list down the elements. If you see the ellipses, the three dots, that means that the list continues indefinitely. In this case, in both direction, infinite. So a set can have an infinite number of elements. I can name a set using letters. For example, in this case, whenever you see Z, that would refer to the set of all integers. Okay, coming from the German word for integer, which is Zinteger. So I know these are all the integers. So that's the collection that I have. So number 1, the word large is subjective, as well as number 2, the word nice is subjective as well. But I know the collection of integers. So I can use the word set. That is how we use the word set. If I use the word set, I'm referring to a well-defined collection of objects. In particular, our objects here are numbers, but these are not limited to numbers. Okay. Next, you can edit your answer and continue the numbering. 1, 2, 3, you're done. Then you add 4, 5, 6. Go ahead. Those who have responded in the first 3 questions, edit the previous answer. And then add 4, 5, 6. Same question. Which collection is a set or not a set? Number 4, the collection of numbers that are both even and odd. The collection, number 5, the collection of numbers that are both positive and negative. Number 6, the collection of numbers that are neither positive nor negative. So make sure you understand the phrase well defined. Okay, go ahead. Edit your answer previously, then add 4, 5, 6. So that you have like one answer, then continue 4, 5, 6. How about the rest? Wala na po. Madami tayo dito. Okay, so let's proceed. So number 4, okay, there is no number that is both even and odd. So I know there are no numbers that belongs to the collection. This collection is empty. Okay, that's a set. It's the empty set. Number 5, collection of numbers that are both positive and negative. I also know that there is no number that is both positive and negative. Empty set, so it's a set. Number 6, a collection of numbers that are neither positive nor negative. Now, I know one number that is neither positive nor negative, and that is 0. 0 is unsigned. 0 is unsigned, okay? So, looking further into the integers, we cannot, okay, include 0 in the negative integers, and we cannot include it in the positive integers. So if I look at the integers and group it based on signs, okay, 0 is neither positive nor negative. So we consider it neutral or unsigned. Therefore, if I group this based on signs, this ellipse or integer looks like this one. So there is, it's like a cracked egg. There is a portion reserved for 0. It's neither positive nor negative. Okay, next. So going further into the concept of integers, okay, we have the idea of subset. Okay, so here, if all elements of a set can be found in a mother set or superset, this set is referred to as a subset. So it's a subset of the bigger set. So I have here three subsets. I can have any number of elements as long as all elements belong to the mother set or superset. That is considered a subset already. Okay, so these three you see here are subsets of the set of integers. So they are not the only subset of the set of integers. There are many more. Okay, next, I can classify my integers based on what we call parity. Parity means either even or odd. Okay, even parity means it's divisible completely by 2, leaving a 0 remainder. Odd parity means the remainder is 1. So in terms of parity, there are only two subsets, odd and even. Okay, take note that when you define the concept, remember mathematics is a precise language. If I say even or odd, I need a definition. For other individuals or laymen, maybe they will define even as a number divisible by 2. But that is a property of an even number. It is not the definition of an even number. The definition of an even number is this: a number x is even if it can be written in the form 2k, where k is an integer. Okay? An odd number, the definition is this: a number is odd if it can be written in the form 2k plus 1, where k is an integer. What does that imply? You get an integer for the value k, then you multiply by 2 that integer. What is generated, so you can say this is a generator or a formula, is an even number every time. So for example, I have k is equal to 0. Okay, 2 times 0 therefore is 0. Because I use the formula 2k, that falls under even. So 0 is unsigned, but 0 is even. So it belongs to the set of even numbers. Now, if k is equal to 0, and I use the formula 2k plus 1 for odd, same value for k, that's 2 times 0 plus 1. 0 plus 1 is 1. Therefore, 1 belongs to the set of odd numbers. You can use other integers and test whether that would be even or odd. Just plug in the formula. So this one is 2k plus 1. So 2k, therefore, by implication, is always divisible by 2. So that's a property of an even number. So that's called parity. Here are other possible subsets of the set of integers. Again, you can think of other subsets. Subsets can have a one element. This one, okay, are other possible subsets. Maybe you're familiar already. I can group together the negative integers. Okay, so look at the notation. It's the letter Z with a superscript minus. Positive integer Z plus. Non-negative integers, positive and 0. So you cannot call 0 either positive or negative. So you just say non-negative. It's also referred to as the set of whole numbers, set of non-positive integers that include 0, and the negative integers. Even, you can use E or you can use O. So a lot more subsets are possible. These are just the common subsets that we use. Okay, now there is a bigger set, bigger than the set of integers. Okay, so that's the ellipse that you see right now. Inside it is the set of integers. So meron pang mas malaki. There is a bigger set. We call it the set of real numbers. There's actually another set bigger than the set of real numbers. Okay, but we'll stick with this set of real numbers for our purposes today. Then, okay, the set of real numbers, okay, I can give two subsets of that. The set of rational numbers, there you go, this one. Okay, so there's a line. Okay, so that's, okay, one subset. And then another subset, we call it the set of all irrational numbers. Here, second to the last, that's the definition of the set of rational numbers. Any number that can be written in the form P over Q, in otherwise in fraction form. Obviously, fractions, okay, you cannot use zero divisors. Okay? So if I can write a number in fraction form, that would fall under the set of rational numbers. P over Q. Except when it provided, so P and Q are integers. Again, mathematics is very precise, so you have to identify where you get P and Q. P and Q are integers. Okay, if you have restrictions, you have to specify. Well, very precise language, rigorous. Okay, so I have a question here. How come the set of integers is a subset of the set of rational numbers when I don't see fractions at all in the set of integers? How do you explain that? Anyone? If you want to use the microphone, just raise your hand first, okay? Why is the set of integers a subset of the set of rational numbers? When I define the set of rational numbers as fractions of the form P over Q, where Q is not equal to 0. Bakit po siya dun sa loob? Okay, other participants, can you explain why the set of integers are considered a subset? of the set of rational numbers. So you see here some examples, correct? So for example, 1/2, that's obviously a fraction, -2/5, 1/3. So all fractions belong to this set. Okay, so it's a subset of the set of real numbers. And then this set, so it's a set, has the set of integers as a subset as well. Okay, so how come it is the set of integers is a subset of rationals? Other answers coming from the audience, please. Okay, 40 tayo dito, 40. Don't be shy. Don't be shy behind MS Teams. Okay. Oh, we have a response from Lay Canog. Because every integer can be expressed as a rational number. Okay, can you specify, Lay? In what way? Okay, the rest you can also send in your answers. Don't wait for your other classmates. Okay, so from Manjot, he gave an example. For example, 9 can be written as a fraction, 27 over 3. You may refer to. Okay, wow. Okay, sige po. Ganun po ba, Lay? Sige. So, we interpret the set of integers if you use a divisor for each integer, specifically 1, then you have written down the set of integers, the integers in fraction form. And so our interpretation is that is why integers are also considered rational numbers. Their default divisor is 1. Correct? So it's a special divisor for them. So therefore, they are also considered rational numbers. Therefore, that's the reason why the set of rational numbers, the set of integers is a subset of the set of rational numbers. So that's the reason why. So puros 1 lang yung divisor nila. Now, what is another interpretation? The set of rational numbers can be said to be the set of all terminating or repeating decimals. So for example, 1/2, that can be written as 0.5. Okay, 1/3, that is 0.333, and so on. We usually say 0.3 bar with a bar above the portion that is repeating. 0.5, we can interpret as a 0.5 with an infinite string of zeros afterwards. That is considered terminating. Okay, the logical connective is or. Or. This is exclusive or because there is no number that is both terminating and repeating at the same time if you attended our logic class. Terminating or repeating. That's the set of rational numbers. While the set of irrational numbers is the set of non-terminating, okay, look at the logical connective, and not or. So that means both non-terminating and non-repeating. For example, pi, that's approximately 3.14. We say approximately because we cannot write it exactly because it is non-terminating and non-repeating. There's no portion in the decimal part of pi that repeats or terminates. Square root of 2, approximately 1.41, same property. Natural number, approximately 2.718, used in the sciences for growth and decay, right? That is the natural number. A lot more, okay? Numbers are found also in the set of irrational numbers. So please take note that we reserve some letters: W, whole numbers; N, natural numbers; Z, integers; Q, set of rational numbers; Q complement, Q with a superscript C denotes the set of irrational numbers. When you see these letters being used, they mean these sets that we are discussing right now. Okay, there to clarify. And then a special set below. This is called the null set or the empty set. You can also use a pair of curly brackets without any element inside to denote the empty set. So there's only one empty set. Let's proceed. Mathematics is also an abstract language or symbolic language. Here are some symbols. Again, English letters to denote a particular set, curly brackets to enclose the elements. This is the Greek letter epsilon. This is used to replace this phrase. It belongs to, is an element of, is a member of, referring to the element. When you see that symbol, read it like it's a phrase in words. Vertical bar or pipe symbol is used when you are declaring an element inside a set, usually for declared rules. I'll show you later. Or instead of that pipe symbol, you can use a colon instead. That is to replace the phrase such that. So why are there symbols in mathematics? Well, there are symbols in mathematics because symbols are efficient. If you know the meaning of the symbol, it holds that meaning without ever writing down the whole phrase or the whole sentence or the whole concept. If you define it that way, you see that symbol, it's more efficient to write the symbol than the whole sentence or phrase. So it's an efficient way of writing. This one is the symbol for the phrase is a subset of. Okay, it's a horseshoe symbol. Horseshoe symbol is a subset of. So read it like it's in words. Okay, here are again examples. Different ways of writing sets. For example, from this group, they are listed. Okay, so the elements are listed. Also referred to as roster method, list method, or roster method. Sometimes that's impossible to do. For example, the set of rational numbers, I cannot write every possible fraction there is. And so I will just set a rule. Set of all x's, you can use a pipe symbol, such that, how is that generated? Well, in fraction form, p over q. Where do we get p and q? From the set of integers. Is division by zero allowed? No. So q is not equal to 0. That is in rule method. So two ways of writing sets: list method or rule method. The rule method is also referred to as set builder notation. Okay, that's also the same in sets E and O, but here we're using that epsilon. Okay, so that means that K is an integer. K belongs to the set of integers. So, okay, so we're using symbolic language there. Next, if ever you need the real numbers between two other real numbers, that means regardless, is it integer, fraction, whatever, if you want every real number between two real numbers, you can switch to this notation. This is referred to as the interval notation. For example, if I want all elements between 1 and 2, regardless of what it is, okay, there, those are the elements there. There are infinitely many real numbers there. inside that interval. So just write it like this using brackets. The brackets indicate that the endpoints are included. If you don't want to include the endpoints, you can use parentheses. So that is an open interval. You can also include the left side or the left end of the interval, but not the right. So bracket on the left, parenthesis on the right. You can include, for example, the right endpoint, but not the left. This is half open intervals, half open or half closed, right? So just in case you will be needing that, you can use that notation. Don't confuse AB with ordered pairs, but the context will be clear, no? Whether you're using that as an interval or an ordered pair. If you recall, that's also how you write ordered pairs using parentheses. Set builder, yes. Set builder as okay. If you use this one, set builder, because that's the rule, right? You specify values of x in between two values. Now, so that you don't have to write that in set builder, okay, that's interval notation. But alternative way, ito. These are the interval notation. This is set builder. Or rule method to, no? So ito, mas prefer natin kasi hindi na ako magsusulat ng x. Okay, next. Another concept regarding sets, we call it cardinality of sets. Okay, so I listed down 4 sets. I named them A, B, C. Okay, cardinality refers to the number of elements of a set. Number of elements of a set is referred to as its cardinality. Letter A is in rule method, set builder. So I don't have to list down the 26 letters. I just said set of all x's, just that x is a lowercase English letter to be specific. Okay, so the notation is you put a double bar. That means you count how many elements are found in the set. That's referred to as its cardinality. If it is listed, just count everything. So cardinality of B is 6. Take note of the difference of sets C and D. Okay, using a strict inequality for set C, using a non-strict inequality in set D. Set of all x's, such that. So you read that as the phrase such that. Let's convert this to list method. Such that x is a positive even number. So 0 is neither positive nor negative, so I cannot include 0. The smallest positive even is 2, then 4, then 6, then 8. I'll stop at 8. Okay? What will I repeat, John Lloyd? You can rewatch the video later on. Another is a recording anyway. So you have set containing 2, 4, 6, 8, and then this one I can continue. So 2 again, 4, 6, 8, but 10 is allowed because that is non-strict. So therefore, the cardinality of set C is 4. The cardinality of set D is 5 because that includes 10. Okay, so two sets can be equal. Take note that disarranging or rearranging the elements in a set does not affect the set. So for example, if I have 1, 2, 3, 4, the set containing set A, And then I have set B, the set containing 1, 4, 2, 3. These are equal sets. The way you write the sequence of elements, okay, doesn't matter as long as the sets are, okay, the sets have this exact same elements, they are equal. Okay. So again, I have already mentioned empty set. There's also one more set called the universal set. Every set we can think of as having a universal set. So when I discuss the set of integers, okay, the universal set is the set of real numbers. Without even mentioning it, that's implied. That's the universal set, the set under discussion. But you can specify, no, in a particular discussion what would be the universal set. So I'll explain that later on when we go to operations. So I'm sure you're familiar with Venn diagrams, visualization of sets. We usually use a rectangle for the universal set and circles or ellipses for the subsets. So when you discuss set under a universal set, all sets are subsets automatically of the universal set. So it will be the biggest set under discussion. So you can, for example, create circles there under the universal set. So some sets can have overlaps. A is a subset of B, as you can see, but all of these sets are automatically subsets of the universal set U. What else? Okay, so this one is a nested set, just like what you see in integers. Okay, 0 is a subset of the whole numbers, correct? Natural numbers. Okay, so whole numbers, then subset of integers, then subset of Q, then Q subset of R, nested. One inside the other. Okay, so for part two of our discussion, we have what we call relationships on sets. There are only three. First is subset. So we're done with this. A set is a subset of another if all elements of that set belongs to the mother set. Equality. Okay, exactly the same elements. Rearrangement doesn't matter. Equality. So let's focus on the second, equivalence. So when are two sets equivalent? Okay. So two sets are equivalent if their cardinalities are equal. So cardinality, right? Number of elements. This works for finite sets. Sets wherein I can count the elements. So if cardinality of x is equal to cardinality of y, then x is equivalent to y using that symbol. That's the tilde symbol. When you see that, you're saying the two sets are equivalent. Okay, so what's important here is the number of elements are the same. The kind of elements doesn't matter. So, for example, you can have set A, okay, contains letters, and then set B, okay, contains numbers like that. Doesn't have to be consecutive or whatever, can be random numbers. But if I count the number of elements in A, the cardinality of A is 5, the cardinality of B is 5. So if they have the same cardinality, then you say that they are equivalent. A is equivalent to B. Okay? If it comes to infinite sets, that's a different thing. For infinite sets, okay, we just use the concept of one-to-one correspondence. There. one-to-one correspondence. So what does that mean? I cannot assign a value if my set is infinite. And so what will happen is I can just map the elements. So let me go back to our discussion on the integers. Remember, the integers can be, okay, grouped into two groups, odd numbers and even numbers. Okay, even numbers are generated by this formula, 2k. So if I add 1 to 2k, that will generate an odd number. So I can go there. So for example, 2, that's 2k plus 1, okay? That is mapped to 3. Another, for example, 0, even, plus 1, 2k plus 1, 1, 0 is mapped to 1. Negative 2, even, plus 1, negative 1 in the odd number. Now you can do that every time because you know the formula for even is 2k, add 1, odd. And that is reversible, vice versa, correct? So if I have an odd number, I can start with odd minus 1, minus 1. So 2k plus 1 minus 1 is equal to 2k. So every 2k plus 1 minus 1 is even. Okay, so I have here 5. 5 minus 1 is 4. 3 minus 1 is 2. Okay, double-headed arrow. That means there is a one-to-one correspondence. There is a one-to-one correspondence between, okay, the set of even and odd numbers. So even if I know the set of odd numbers is infinite and the set of even numbers is infinite, I can map each element, okay, in a one-to-one correspondence. They have the same number of elements, right? So therefore, the set of even is equivalent to the set of odd numbers. Technically, that works as well if it is finite. And so the definition of equivalence uses one-to-one correspondence. Naintindihan po? Do you understand that concept? So whether the set is finite or infinite, as long as I can map each other's elements together, they have the same count. So therefore, they are equivalent. Okay, we're done with equality. Okay, so last part of our session for today is operations on sets. I'll show you Venn diagrams to make it easier to understand. So what are operations on sets? Analogy, operations on numbers. I can add two numbers, get another number. I can subtract two numbers, get another number. I can multiply and so on and so forth. But these operations are for sets. So we call them set operations. Okay, I listed down 7, but I think we can reach until number 6 today. Okay, let's start. So I have here two sets. I named them X and Y. X is the set containing 0, 1, 2, 3, 4, 5. Y is the set containing 4, 5, 6, 7, 10. Okay, so let's deal with set union. I have two circles. This rectangle is our universal set. Okay, so that's just a bigger set where we get our sets. So I don't need to specify that. So that's the rectangle there. Okay, observation 4, 5. These are common to both. So I'll put here in the overlap. Now, what else is captured by set X? 0, 1, 2, 3, but that is not captured by Y. So I'll place it here like that. 0, 1, 2, 3, 4, 5. Okay. Y on the other side, 4, 5, 6, 7, 10. So I'll place 6, 7, 10 on that side, right? So if I look at the sets, they have common elements. The way we write union is like letter U without a tail. This is okay. The elements in X or okay logical connective in Y, or here is inclusive or. So if you attended again our logic, because it allows for an overlap. True, each true or both true, pwede. So elements in X or in Y or both X and Y, pwede po. So if I shade this, that's the union. If I list this 0, 1, 2, 3, 4, 5. But since 4, 5 is an overlap, no common to both, I don't need to repeat this 4, 5 because it's already represented. So I'll just continue. 6, 7, 10. Okay? Take note that property X union Y is equal to Y union X. The order is not okay. I can swap the roles. You'll give the same result. But also, one property is number 2, cardinality of X union Y is equal to cardinality of X plus cardinality of Y minus cardinality of K X intersection Y. So we'll deal with that in the second slide. So what is intersection? So the intersection is the, okay, there's a symbol, elements in X and then and in Y, common to both. So in this case, the set containing 4, 5. Okay, let's go back. Take note that in this case, the cardinality of X is 6. The cardinality of Y is 5. Tama po. Excuse me. Now, if I list the elements, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Correct? So the actual is 9. So I cannot simply add together the elements in the union because that would be overcounted. Okay, that's overcounted because 4, 5 are both included in each set. So correction for overcounting. I will now subtract the cardinality of the intersection. So X intersection Y, cardinality, okay, of this set is 2. 11 minus 2, that is 9. So this is called principle of inclusion, exclusion, PIE for short. Correct? So the correct counting for union is Principle of inclusion, exclusion, PIE. Yan. May subtraction pa pala yan dulo. No? In case there is no overlap, that would be 0. So therefore, the cardinality is straightforward if there is no intersection. But if there is, you're not sure, you have to use PIE, principle of inclusion, exclusion. Okay, just like set union, if I get the intersection of x and y, that is y intersection x. So in this case, the shaded is just the overlap. Next, set difference. Okay, so x minus y is the symbol. Elements in x, but not in y. What does that mean? Okay, you get the elements in x, except those you can also find in y and delete them. Okay, that means for 5, okay, elements in x, okay, for 5, I can also find in y. And so this means that the answer to x minus y is 0, 1, 2, 3. Delete for 5. Now, I can have y minus x. This means that these are elements in x, but not in elements in y. So the first set is important, but not in x. So ang masusunod yung laman ni y. How about yung 6, 7, 10 kanina? They don't have any effect. Yung mga sobra, the excess numbers doesn't have any effect. Only the common numbers are deleted. So in this case, yung laman ni y ang masusunod. But since I have 4, 5, 6, 7, 10, delete 4, 5, what's left is 6, 7, 10. That is when you have y minus x. Okay, obviously in this example, you can say x minus y is not equal to y minus x. In general, x minus y is not equal to y minus x. Special case, okay, give me the condition. X minus y may be equal to y minus x. Okay, go ahead. What is the condition? When is x minus y equal to y minus x? When is x minus y equal to y minus x? In general, they are not, obviously, because the first set will be the set that will be followed. Tatanggalin mo na lang yung laman na makikita mo doon, ano? But it's possible x minus y is equal to y minus x. Can you give me the condition when that happens? Okay, sige po. Type in your response, please. In the chat box. Kailan kaya magiging equal sila? In general, hindi. In general, x minus y is not equal to y minus x. But sometimes, yes. Okay, give me an idea. Give me an idea when x minus y will be equal to y minus x. Anyone from the audience, please? Go ahead, don't be shy. What condition do I need to check? So there is an answer from Jervik. Both sets are empty. Okay. Pwede rin hindi empty as long as the sets are, anyone? Kailan pa? Uh, so separate, we don't, okay, so the words must be very specific. Sets are, okay, from Matthew, same. Okay, so make this more specific. So, okay, so no, if the sets are, if the sets are not equal, if you mean that, y x minus y is not equal to y minus x. Identical. Okay, sige. So, use specific or clear terms. Again, math is precise, huh? So, this is the answer. If x is equal to y, then x minus y is equal to y minus x. So, for obvious reasons. However, if x is equal to y, x minus y is actually empty because you have to delete everything. Tama po ba? Y minus x as well. So therefore, if the two sets are equal, x minus y is equal to y minus x. If the two sets are not equal, then x minus y is not equal to y minus x. Okay, so I referred to y minus x. Okay, referring to shading, I'll shade this. This is x minus y, except the overlap. Y minus x, I'll shade this. That is y minus x in the Venn diagram. So the overlap is intersection. Shade both, including the overlap, is union. Shade one side is set difference. X minus y on the left, y minus x on the right. See? So these are the operations. Next is set symmetric difference. Okay. Now, the word symmetric means symmetric. This side, at the same time, this side is shaded. Okay. So what is that? Symmetric difference is the set of elements, okay, except the intersection. And so therefore, it's x minus y union y minus x. That's why it's referred to as set difference, symmetric difference. If I list down the elements of x minus y, we have 0, 1, 2, 3. Y minus x, we have 6, 7, 10. Take the union, we have 0, 1, 2, 3, 6, 7, 10. Okay, take note that if I first get the union, x union y, then subtract the intersection, this will give me the same result. Okay, let's try. Union 0, 1, 2, 3, 4, 5, 6, 7, 10. Union minus intersection, set containing 4, 5, delete 4, 5. Then we get 0, 1, 2, 3, 6, 7, 10. Okay? So as you can see, they give the same result. This is called symmetric difference. Sino to? Direct iba nga. Ngayon lang attend. Patapos na. Okay, make sure you attend class on time. Patapos na tayo. Ngayon lang kayo nag-enter. Okay, complement of a set. You have the universal set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let that be the universal set. This is complement of a set. So there is a question from Andre Callow. Paano po pag x minus y intersection y minus x empty? Okay, good question. Let me go back. Because they do not have any elements in common. So, x, lagay natin sa property. So take note, x minus y intersection y minus x is empty. These are called, so no elements in common, are disjoint sets. Correct? Kasi hindi sila magmi-meet dun sa overlap. So, empty, wala. Intersection na. Other questions? Na-disconnect. Okay. Sorry na. Okay, so you have the set, the universal set. Okay, there. Imagine that's the rectangle. And then I'm thinking of X here, the blue circle. It contains 0, 1, 2, 3, 4. So superscript C, X complement. So the set of elements not belonging to X. So by default, X is a subset of the universal set. So that means it's 6, 7, 8, 9, 10. Complement, yung natira. Universal set, say this is Y. Y complement, this is the set containing 0, 1, 2, 3. Okay. So 4, 5, 6, 7 included in Y. 8, 9 hindi. So kasama siya sa complement. There. Diba? So ito po ay, so yung X complement po ay universal set minus X. Tama pa? That's set difference. Now, for set difference, X and Y may not be related, in fact. But for complement, the set is always a subset of the universal set. Always. Complement. But you can say it's also set difference. Just a special set difference. Universal set is being used. Another property, X complement is X. The complement of the complement is the original set. Okay, one last cross product. So for example, you have XY there. So ang laman nito ay ordered pairs. Okay, there. It doesn't have numbers as the elements. The elements are ordered pairs. Okay. So that's the symbol, X cross Y. All you have to do is to pair. 0, 0, 0, 1, 0, 2, 0, 3. Pair, ordered. 0, 0, 0, 1, 0, 2, 0, 3. Okay, before you move on to the next element, exhaust the pairings. Next, move to 1, repeat. 1, 0, 1, 1, 1, 2, 1, 3. 1, 0, 1, 1, 1, 2, 1, 3. Next, 2, 0, 2, 1, 2, 2, 2, 3. Finally, last row, 3, 0, 3, 1, 3, 2, 3, 3. Okay, so if you plot it here, 0, 1, 2, 3, 0, 1, 2, 3. This is Y, this is X. 0, 0, 0, 1, 0, 2, 0, 3. 1, 0, 1, 1, 1, 2, 1, 3. 2, 0, 2, 1, 2, 2, 2, 3, etc. So it's like a set of dots in the XY plane. Ano? If you use integers. If you use integers. Okay, so it depends on which comes first, right? So ang property niyan, hindi equal yung X cross Y kay Y cross X. Tama po. One more property, yung cardinality ng X cross Y ay equal sa cardinality ng Y cross X. Oh, understand that, ha? Hindi equal yung X cross Y sa Y cross X because mauuna yung elements ng first set. Pag binilang mo, parehas lang yung bilang nung laman ng X cross Y at Y cross X. Because ang cardinality ng X cross Y ay cardinality ng X times cardinality ng Y. So ito, 4. Cardinality of X. Y, cardinality 4. 4 times 4. 16 ordered pairs. 4 times 4. 16 ordered pairs. Cardinality niya yun. Ano? Okay, so again, thank you very much for attending. So attendance, please. Type in your name. Go ahead. In the chat box. Thank you very much, everyone, for attending. We're done for today. Recording afterwards in MS Teams. Bye for now.